If we take a closer look at the orbital structure of benzene, we find that the cyclic, delocalized pi electron cloud is loosely held above and below the plane of the benzene ring. The resonance stabilization of benzene is due to the delocalization of these pi electrons. This structural arrangement makes the loosely held pi electrons available for electrophiles, the electron-seeking reagents. Thus, the substitution reactions in benzene are electrophilic in nature. Hence, we can conclude that benzene undergoes typical electrophilic substitution reactions due to the retention of resonance stabilization of the ring, that is, aromaticity. Some common electrophilic substitution reactions of benzene are halogenation, nitration, Friedel-Crafts alkylation, Friedel-Crafts acylation, and sulfonation reaction. Before we proceed into the detailed study of each type of reaction, let us have a look at the mechanism of a general electrophilic substitution reaction. A general electrophilic substitution reaction involves 3 steps. They are generation of the electrophile, formation of carbocation, a sigma complex intermediate, and removal of proton from the carbocation sigma complex. Now, let's take a closer look at each type of electrophilic substitution reaction along with the mechanism in detail. First, let us take up halogenation reaction. The replacement of a hydrogen atom by a halogen atom such as fluorine, chlorine, bromine, and iodine in a benzene ring is called halogenation of benzene. Let us discuss chlorination and bromination, which occur at a temperature between 310 and 320 Kelvin. Usually, the halogenation takes place in the presence of a Lewis acid such as anhydrous aluminium chloride or ferric chloride or ferric bromide, as they help in the generation of electrophile, that is, halonium ion. When benzene is treated with chlorine in the presence of anhydrous aluminium chloride, it results in the formation of chlorobenzene. Let us discuss the mechanism of this reaction. First, an electrophile, that is, chloronium ion in this case, is generated when anhydrous aluminium chloride combines with the attacking reagent chlorine, as shown here. In the second step, chloronium ion attacks the pi electron cloud of benzene ring and forms the less stable intermediate called sigma complex or rhenium ion. The sigma complex, which is stabilized by resonance, is shown here. Note that the second step is always a slow step or a rate-determining step, as the aromaticity is lost with the formation of sigma complex. This is because in the sigma complex, one of the carbon is sp3 hybridized and the delocalization of electrons is not possible. In the last step, the proton is removed from the intermediate sigma complex in the presence of nucleophile AlCl4- ion. This results in the formation of chlorobenzene. Note that the last step of the reaction is always a fast step, as the non-aromatic sigma complex is converted to aromatic compound. Now let us look at nitration. When a hydrogen atom in the benzene ring is replaced by a nitro group, it is known as nitration. Nitration is carried out by heating benzene at about 330 Kelvin with the nitrating mixture consisting of concentrated nitric acid and concentrated sulfuric acid. When benzene is treated with nitrating mixture, it results in the formation of nitrobenzene. Let's discuss the mechanism of this reaction. First, an electrophile, that is, the nitronium ion here, is generated when sulfuric acid transfers a proton to nitric acid, as shown in these reactions. The reaction between sulfuric acid and nitric acid is an acid-base reaction in which relatively stronger acid, sulfuric acid, acts as an acid, whereas nitric acid, which is relatively a weaker acid, acts as a base. In the second step, nitronium ion attacks the pi electron cloud of benzene ring and forms the less stable intermediate called sigma complex or arenium ion. In the last step, the proton is removed from the intermediate sigma complex in the presence of the nucleophile HSO4- ion. This results in the formation of nitrobenzene. Now let's look at Friedel-Crafts alkylation reaction. When the hydrogen atom in a benzene ring is replaced by the alkyl group, it is known as alkylation reaction. When benzene is treated with alkyl halide in the presence of anhydrous aluminium chloride, it forms alkyl benzene. This reaction is known as the Friedel-Crafts alkylation. For example, when benzene is treated with methyl chloride in the presence of anhydrous aluminium chloride, it results in the formation of methyl benzene or toluene. Similarly, benzene reacts with ethyl chloride in the presence of anhydrous aluminium chloride to form ethyl benzene. Let's discuss the mechanism of this reaction. First, an electrophile, which is a carbocation here, is generated when anhydrous aluminium chloride combines with the attacking reagent ethyl chloride, as shown here. In the second step, the carbocation attacks the pi electron cloud of benzene ring and forms the less stable intermediate called sigma complex or arenium ion. In the last step, the proton is removed from the intermediate sigma complex in the presence of the nucleophile Cl- ion. This results in the formation of ethyl benzene. It is important to note that in Friedel-Crafts alkylation reaction, when benzene reacts with N-propyl chloride, isopropyl benzene instead of N-propyl benzene is formed. This is due to the fact that the less stable primary carbocation formed in this step rearranges to a more stable secondary carbocation. Hence, is the result. Now let's look at the acylation reaction. When the hydrogen atom in a benzene ring is replaced by the alkyl group, it is known as acylation reaction. When benzene is treated with acyl halide or acid anhydride in the presence of anhydrous aluminium chloride, benzene forms acylbenzene. This reaction is called the Friedel-Crafts acylation. For example, when benzene is treated with acetyl chloride in the presence of anhydrous aluminium chloride, it forms acetophenone and hydrochloric acid. Let's discuss the mechanism of this reaction. First, an electrophile, that is, the alkylum ion here, is generated when anhydrous aluminium chloride combines with the attacking reagent acetyl chloride, as shown here. In the second step, alkylium ion attacks the pi electron cloud of the benzene ring and forms the less stable intermediate called sigma complex or arenium ion. In the last step, the proton is removed from the intermediate sigma complex in the presence of nucleophile AlCl4- ion. This results in the formation of acetophenone. Similarly, benzene reacts with acetic anhydride in the presence of anhydrous aluminium chloride and forms acetophenone and acetic acid. Next is sulfonation reaction. When the hydrogen atom in a benzene ring is replaced by the sulfonic acid SO3H group, it is known as sulfonation. Usually, sulfonation reaction is carried out by heating benzene with fuming sulfuric acid or oleum, a concentrated solution of sulfur trioxide in sulfuric acid. Sulfonation can also be carried out by treating benzene with chlorosulfonic acid. Note that during electrophilic substitution reactions, if an excess of electrophilic reagent is used, then further substitution reaction may occur in which the other hydrogen atoms of benzene may also be successively replaced by the electrophile. For example, benzene, on treatment with an excess of chlorine in the presence of anhydrous aluminium chloride in the dark, gives hexachlorobenzene. Let's move on to the next type of chemical reaction, addition reaction. Addition reactions occur under drastic conditions at high temperature and pressure. For example, benzene reacts with hydrogen in the presence of a catalyst such as nickel or platinum at 473 to 573 Kelvin under pressure to form cyclohexane. Benzene reacts with chlorine or bromine in the presence of ultraviolet light to form benzene hexachloride or BHC. BHC is used as an insecticide and sold under the names of gamma-axane or lindane or 666. Next, let's discuss the oxidation or combustion reaction of benzene. Usually, aromatic hydrocarbons are stable and not readily oxidized. Hence, on heating in the presence of air or oxygen, benzene burns to produce carbon dioxide and water along with a sooty flame. The presence of higher carbon content than the hydrogen content in benzene produces the sooty flame. Moreover, this sooty flame test is used as an identification test to distinguish aromatic from aliphatic compounds.